Hello everyone, my name is Rahul Moore and today I am going to be teaching electrostatics. Electrostatics is the first chapter in electromagnetism, after which we will learn capacitors, current electricity, magnetic field, electromagnetic induction, alternating current and finally electromagnetic waves. So in electromagnetism we will learn mostly about charge. We will deal with charge. Now what is charge? Charge is that property of a body by which it can generate electric fields or magnetic fields or radiate electromagnetic waves under different conditions. So, charge is that property of a body by virtue of which it can generate electric fields, magnetic fields as well as electromagnetic waves under different conditions. So, let us see these conditions. When charge is at rest, then it will only generate electric field. That is, the electric field will not be zero. When charge is at rest, it will only generate electric field, but it will not generate any magnetic field. So the magnetic field will not be produced. Now, if the charge moves with constant velocity, then it will generate an electric field as well as a magnetic field. If the charge moves with constant velocity, it will generate both electric and magnetic fields. But if the charge starts accelerating, then once again it will produce an electric field, it will produce a magnetic field, but here it will also start emitting electromagnetic waves. Now, what are electric fields and magnetic fields and what is electromagnetic waves? We will learn in different sections. But in our electrostatics chapter, statics, the charge would be at rest. So in electrostatics, we will be dealing with this condition mostly, where the charge will only generate electric field and no magnetic field. So let us begin. Okay, let us begin electrostatics. First of all, let us know a few things about charge. Few basic things like what is the unit of charge? You must have learned about this. It is Coulomb. This is the SI unit of charge. Alright. How many types of charge are there? There are two types of charge, positive and negative. Positive charge will repel each other as well as negative charge will repel each other. Or we can say that like charges, that is the same type of charges will repel each other. What about different type of charges? Positive, negative, they will attract each other. Very basic things, alright? Now, let us see a few properties of charge. First property is charge is scalar. Charge is not a vector. It does not have any direction. Charge is just a scalar quantity. Second, the smallest unit of a charge, is E. The smallest unit of charge is E. Now, what is E? E is equal to the charge of electron or that of a proton, and its value is 1.6 into 10 to the power minus 19 Coulomb. So this is the smallest unit of charge. Now let us understand what does this mean. If a body is charged, if a body has some charge, it will at least have this much charge. It can be positive or it can be negative, but a body, if it is charged, it will at least possess this much amount of charge. It cannot possess anything less than that. Alright? Or we can say, if we are transferring charge from one body to another, then this is the minimum amount of charge which we can transfer from one body to another. Alright? Next property. Charge is quantized. Charge is quantized. What do you mean by charge is quantized? Suppose I have two neutral bodies. They are neutral, that is the net charge on them is 0. How can the net charge be 0? Because this body has an equal number of protons as well as electrons. Similarly, this body has an equal number of protons and electrons. So the net charge is 0. Alright. Now if I transfer one electron from here to here, if I transfer one electron from this body to that body, this body has one electron extra. So its net charge is minus E. Alright. And this body has one electron less. So its net charge is plus E. Alright. Okay, let me transfer one more electron. One more electron. Now its charge is minus 2e and its charge is plus 2e. If I transfer another electron, its charge is now minus 3e and its charge is plus 3e. Clear? Now, my question to you is, can this body possess a charge something like 1.6 electron volt? And this 1.6 plus 1.6e. Can these charges be possible? Now, in order for this body to have this much charge, I'll have to transfer charges equal to 1.6 times of an electron from here to here. But we know that the smallest charge we can transfer is E. For this body to have this much charge, I'll have to transfer 1e. And then I have to transfer 0.6 E, right? But we already know that the smallest unit that we can transfer is E. So we cannot transfer 0.6 E. So this body cannot have this charge, and neither can this body have this charge. Can this body have something like minus 2.3 E charge? Can these charges be possible? Again, for this body to have this much charge, I'll have to transfer 2 electrons and then I'll have to transfer 0.3 electrons. But again, we know that we have to transfer at least this much amount. We cannot transfer anything less than that. So again, these charges are not possible. So we have to transfer in terms of number of electrons. We have to transfer like that. So this charge, the body's body can have 1e, 2e, 3e, 10e, 10,000 e charge. Something like that, but it cannot have such charges. That is, charge on any body will always be an integral multiple of E. Charge on any body will always be an integral multiple of E. It can be positive or it can be negative, but it will always be an integral multiple of E. This is what we mean by charges quantized. Alright. One more property. Consider this once more. If I ask you to calculate the net charge on this system, I have considered this as a system considering the both bodies, what is the net charge before I started transferring? Before I started transferring, both were neutral, so the net charge was neutral. After I transferred one electron, what is the net charge? Again, 0. Net charge is 0. Now, again 0. Now, again 0. The net charge remains conserved. The net charge remains conserved. So we can say that in an isolated body, or in an isolated system, a better word is a system, in an isolated system, isolated means nothing can go from inside to outside, nothing can come from outside to inside. So in an isolated system, the net charge remains conserved. You can write it here. In an isolated system, the net charge remains conserved. The net charge remains conserved or constant. Let us now study Coulomb's law. Coulomb's law. Coulomb's law gives us the force between two point charges. Coulomb's law gives us the force between two charges. Alright? So these are two charges Q1 and Q2. They are of the same nature, so they will repel each other. And if they repel each other, they will exert a force on each other. Q2 will exert a force on Q1 along this direction. Q1 will exert a force on Q2 along this direction. How do we denote this? This is the force acting on 1 due to 2. This is the force acting on 1 due to 2. And this is the force acting on 2 due to 1. This is the force acting on charge number 2 due to charge number 1. This is how we denote it. What if one is positive and another is negative? What if? So they will start attracting each other. So they will exert a force like this. This is the force acting on 1 due to 2. And this is the force acting on 2 due to 1. Okay? Coulomb's law states that these two forces are equal in magnitude. And these two forces are opposite in direction. Coulomb's law states that these two forces are equal in magnitude and opposite in direction, and they are electrostatic force of the same nature. Equal in magnitude, opposite in direction, same nature, acting on two different bodies. Have you heard this before? This is action-reaction pair. Electrostatic force is an action-reaction pair. Electrostatic force is an action-reaction pair. From Newton's third law, electrostatic force is an action-reaction pair. We will learn what is the expression for Coulomb's law, but just by this property we can start forming questions. We can start forming questions just by this single property. Let us take an example. Suppose I have two charges, A and B. Let's say 2 Coulomb and 3 Coulomb. Let their masses be 2 kg and 4 kg. They are released. Now what will happen? They are of the same nature, so they will start moving away from each other. They will repel each other, so they will start moving away from each other. As they move away, their speed will start increasing. What is, if after some time the speed of A becomes, let's say, 5 meter per second, what is the speed of B? If after some times the speed of A becomes 5 meter per second, then what is the speed of B? Let us see. Now we know that electrostatic force is an action-reaction pair. They will exert equal and opposite forces on each other. So what is the net force on the system? Net force on the system is 0. Net force on the system is always 0. And if net force is 0, what is momentum? Momentum is conserved or constant. Momentum would remain constant. That means initial momentum would be equal to the final momentum. Alright? Initial momentum would be equal to the final momentum. Now initially it was at rest. So initial momentum is 0. What is the final momentum? I am taking this direction as positive, this direction is negative. Vector quantity. Momentum is a vector quantity. So what is the final momentum? 4v. This is in the negative direction. 2 into 5 minus 2 into 5. So calculating, we will get our answer as 10 by 4 meter per second. Alright. So in this way, different section of mechanics can be used in electrostatics. Okay. Now let us see the expression for Coulomb's law. Let us see the expression for Coulomb's law. Suppose we have two charges Q1 and Q2 separated by a distance r. Suppose we have two charges Q1 and Q2 separated by a distance r. The force which acts between them, is proportional to the product of the two charges. And inversely proportional to the square of the distance between them. This is what Coulomb's law states. The force which acts within them is proportional to the product of the two charges, as inversely proportional to the square of the distance between them. And after this relation is equated, it comes out to be like this, where K is a constant. K is a constant known as Coulomb's constant. K is a constant known as Coulomb's constant, and its value is 9 into 10 to the power 9 Newton meter square per Coulomb square. How did I get this unit? From this formula. K, you can see Newton meter square per Coulomb square. Very easy. Now, you can calculate the dimensions of K at home. You can try this. One more small thing to note is K is also equals to 1 by 4 pi epsilon naught, where epsilon naught is known as permittivity of free space. Permittivity of free space. And its value is 8.85 into 10 to the power minus 12. What would be its unit? Its unit would be opposite to that of K, that is Coulomb square per Newton meter square. You can also calculate the dimensions of epsilon naught. Alright. So this is Coulomb's law, the expression for Coulomb's law. Now, after some time, we will learn what is Coulomb's law in a medium and what is the vector form of Coulomb's law. But just by this expression, we can form a number of questions, a variety of questions. So let us begin. Okay, before we start, there is one more property that I would like to state. Suppose I have two charges, Q1 and minus Q2. So they will exert a force on each other. Force on 1 due to 2. Force on 2 due to 1. If I bring another charge in the picture, if I now bring one more charge in the picture, will this force get affected in any way? The force between these two charges, will it get affected by this charge? No. This is the property. Yes, definitely this will exert one more force here. Force on 1 due to 3. But this force will not get affected. This force will not get affected. The property is the force between 2 point charges. The force between two charges is independent of the presence or absence of other charges. If I bring one more charge here, it will again exert a force on this, but this magnitude, this force magnitude will not change, and neither will this change. The force between two charges does not depend on the presence or absence of other charges. Alright. Now let us begin with the questions. Let us start with some of the questions. So, electrostatics can be combined with different sections to form different types of questions. Let us combine electrostatics with vectors to form some questions. Let us see. Suppose I have 3 point charges placed along an equilateral triangle. I have 3 point charges placed along an equilateral triangle of side A. Okay? What is the net force on this charge? What is the net force on this charge? Alright. From Coulomb's law, we know that this charge will exert a force along this direction. They will repel, same nature. Similarly, this charge will exert a force along this direction. How much force will this charge exert on this? Let's say this is force F. What would be F? K, Q1, Q2, that is Q square by distance square, that is A square. This is F. What would be the force exerted by this charge on this charge? If you see carefully, it will again be F. K, Q1, Q2, Q square by distance square, A square. Both will exert the same type of force. So will the net force be 2F? No. The force is a vector. We have to apply vector addition. The angle is equator triangle, so 60 degrees, 60 degrees. What would be the net force? from vector law of addition, we know net force will be F1 square plus F2 square plus twice F1 F2 cos of the angle between them. And if you solve this, you will get the answer as root 3f or root 3 kq square by a square. Okay? Alright, let us do one more question. Now, let us see, if I take a square and put 4-point charges at its vertices, this is a square of side A. This is a square of side A. Now, there is one more charge at the intersection point of its diagonals. There is one more charge at the center. What would be the net force on this charge? What would be the net force on this charge? Okay. This charge will exert a force along this direction. This charge will exert a force along this direction. Again, this charge will exert a force along this direction, and this charge will exert a force along this direction. Okay? Now, what is the force between these two charges? Let us call it F. Can you calculate F? Between these two charges? K, Q1, Q2 by distance square. If this is A, then this is root 2A, then this is A by root 2. So F is 2K Q square by A square. Can you tell me what is the force between these two charges? It will again be F. Why? Same charges, same distance. Again, between these two charges, it will be F. These two charges, the force is F. So, F, 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 F. They will get cancelled out, and the net force would be 0. The net force would be 0. Let us take one more question. Okay. What if I say that this charge is minus Q? Now what would be the net force on the central charge? Now what is the net force on the central charge? Now, if you see carefully, these two charges will again repel and cancel out. But now this will repel, but this will attract. So they are along the same direction, they will not get cancelled out, and the net force will become 2F. What is F? We can put it. Alright, so this is the net force now. We can do one more question here. What if I say this is also minus Q? Then what? Then what is the net force on the central charge? What is the net force on the central charge? What is the net force on the central charge? Now, what would happen? Two forces will act along this direction, and two forces will act along this direction. Okay, so this will be something like this. And what is the angle between them? It is 90 degrees. So the net force by vector addition under root f1 square plus f2 square plus 2f1 f2 cos of the angle between them, cos 90, you will get it as root 2 times of 2f. That is, if you put the value of f, 4 root 2 kq square by a square. So in this way, different types of questions can be found pentagon, hexagon, etc. And you can be asked to calculate force on any one of the charges. Simple vector addition. Okay, let us see the next type of questions. Electrostatics can be combined with series to form different types of questions. Let us see. Suppose this is the x-axis, this is the origin, and I have placed 1 Coulomb charge at the origin, and then at 1, 0 there is 1 Coulomb charge, at 2, 0 there is 4 Coulomb charge, at 3, 0 there is 9 Coulomb charge, up to 10, 0. Can you guess what is the charge placed here? If you see closely, this is 1, 1 square, 2, 2 square, 3, 3 square. So here it will be 10 square, 100 Coulomb charge. This is a pattern. Alright? And we are asked to find the net force on this charge. The net force on the charge placed at origin. So let us see how to do this. This charge will repel. This charge will also repel. This charge will also repel. If you see, all the charges are repelling in this, so the forces are in the same direction. The forces are all in the same direction, so we can simply add those forces. We can simply add, and we can take out k as common, because k will be common in all the terms. Okay, now what is F1? K Q1 Q2, 1 into 1 is 1 by R square 1 square. Next, F2, K Q1 Q2, Q1 Q2, 4 by R square 2 square, plus third force is K Q1 Q2, 9 by R square 3 square, up to F10 would be, can you guess? K Q1 Q2, 100 by R square 10 square. If you see, they are getting just cancelled out, and it would be like 1 plus 1 plus 1 up to 10 times. 10 times. So it would be 10k. Okay, so this is a series type of question. Let us do one more. Let us do one more. If I say I have 8 Coulomb here, 27 Coulomb here, can you guess what would be the charge here? See, this is 2 cube, this is 3 cube, so we will have here 10 cube, that is 1000 Coulomb charge. Alright? Same question, net force on the charge at origin. Net force on the charge at origin. Okay, let us see. Again, all the forces are in the same direction. Simple addition. K common. These two charges. K Q1 Q2 1 by R square 1 square. This two. Q1 Q2 8 by R square 2 square. Okay. Next term. Q1 Q2 27 by R square 3 square. Okay. Next, what would be the last term? Q1 Q2 1000 by 10 square. If you see properly, this is 1, 4 2 jar. This is 2, 9 3 jar. This is 3, up to 10 10 jar. Sorry, 110 jar. This is 10. Alright. So this is like sum of n natural numbers. Do you know the formula? 1 plus 2 plus up to n natural numbers if added. The formula is n plus 1 by 2. So what would be our answer here? 10 plus 1 by 2, that is 55k. This is our answer. Similarly, I could have taken here 16 Coulomb, 81 Coulomb and so on. Then we would have gotten 1 square plus 2 square plus 3 square. So that would have been another formula. Okay? Let us do one more. A little different. Not different, just different series. 1 Coulomb, minus 2 Coulomb, 3 Coulomb, 4, 0, I have minus 4 Coulomb and so on up to infinity. Okay, infinite number of charges are placed. Now what would be the net force on the charge at origin? What would be the net force? What would be the net force on the charge at origin? Okay. Now if you see, this charge will repel, but this charge will attract. Again this charge will repel, but this charge will attract, and so on. Repel, attract. So they are in different directions. They are all in different directions. I mean, one is this side, another is this side, and then again this side, then again this side. So opposite directions. Now, how to calculate this? We know I am taking this direction as positive. I am considering this direction as positive. Just you can consider that direction as positive. It doesn't matter much. Okay. So what is the force between these two charges? K I have taken common. Q1 Q2 by R square. Alright. This I have taken as positive. What is the force between these two charges? Q1 Q2 by R square. But since this is in this direction, I have taken it as negative. Okay. What about these two charges? This direction. So Q1 Q2 by R square. These two charges Q1 Q2 by R square up to infinity. Okay. So this looks something like this. Okay. Have you seen this type of expression before? In your mathematics class maybe. Have you seen this expression? ln 1 plus x. What is this? It is equals to x minus x square by 2 plus x cube by 3 and so on up to infinity. Okay. Now if I put the value of x as 1, this will become ln 2. This will become ln 2 and this will become 1 minus 1 by 2 plus 1 by 3 up to infinity. Can you see that this expression is the same as this expression? So I can just write it as k ln 2 and this is our answer. So in this way, different type of series can be used with electrostatics to form variety of questions. Let us move to the next pattern. Let us move on to the next pattern. What if I combine electrostatics with kinematics? Basic kinematics. Suppose I have two charges, Q and again charge Q, mass M, and I keep this charge as fixed. That means this charge will not move. Okay, and it is at distance, let us say R1 distance, and I release this charge. This charge is released, so it will start moving away due to repulsion. When it reaches a distance R2, what will be its speed? What will be its speed? Okay, two charges, one is fixed, one is released, it starts moving away. When it reaches a certain distance, what is its speed? Alright. First of all, this question can very easily be solved with the help of energy conservation, but since we have not learned electrostatic potential energy yet, we will do it with basic kinematics. Let me consider just a general position. Okay, at a distance, let's say r. A general position when this charge is here. What is the force acting on it? K q square by distance r square. Okay. So what would be its acceleration in this position? Force by mass. Force by mass. So I'll get this force upon mass. Now, can I use equations of motion here? Can I use equations of motion here? V square equals to u square plus 2as. Can I use that? No, I can't. Why? Because acceleration is not constant. Equation of motion can only be used if acceleration is constant, but here acceleration depends on r. As r increases, acceleration will change, it will decrease. So we cannot use equation of motion, so we have to go by basic kinematics. Basic kinematics says that A can be written as dv dt. But is it should we write it as dv dt? Time is nowhere mentioned, nor it is asked. There is no point on introducing another variable. Why shouldn't we write it as dv dx, v dv dx, or v dv dr in this case? Okay. K q square by m r square. Now it's simple calculation. I can put it like this, rearranging v dv equals to k q square by m dr upon r square, integrating. What would be the limits? R goes from r1 to r2. R goes from r1 to r2, and v goes from, what is its speed here? When it is at r1, its speed is 0. It is just released. And at r2, we have to find out. Okay? v dv, v square by 2, 0 to v, kq square by m, 1 by r square integration is minus 1 by r, r1 to r2. So we get v square by 2 equals to kq square by m, 1 by r1 minus 1 by r2, and then we can find v. Okay, so in this way different types of questions can be found with kinematics, with series, with vectors. Okay, so in the next class we will do some more questions and we'll learn the vector form of Coulomb's law as well as Coulomb's law in a medium.